So good afternoon, everyone. My name is Radu Weiss. I'm a software development manager working on Firecracker. And in today's session, we are going to recap what Firecracker is. Then I will then I will look at what's happened with Firecracker in the year since we have open sourced it at reInvent 2018. And I will also later talk about our roadmap. Sebastian will tell you all about how Firecracker is used at Weaveworks. And then my colleague Alexandra will focus on snapshotting, which is an upcoming feature for next year. With that, let's get started. If you looked at EC2 instance launches over the past couple of years, you probably noticed they got more frequent and also covering a broader range of use cases. Part of that has got to do with the deep investments that we have been making in platform technology, both on the hardware and on the software side. And Firecracker is part of this story. It's a long-term investment that AWS is making in serverless platforms. What is it exactly? It's basically, in a nutshell, it's a lightweight virtualization technology that is a flexible yet secure barrier around customer workloads. An easy way to imagine it is basically if you run code in Lambda or if you run containers, you can have this security barrier around your workload, and then on the same physical server, there are many more of these execution environments. All of them isolated from each other, and let's say sharing the hardware resources of that machine in a very efficient way. We built Firecracker from the ground up to serve this exact purpose. We started in 2017. It's been in production since 2018. And currently, AWS Lambda runs trillions of function invocations per month in Firecracker execution environments for hundreds of thousands of customers. So let's take a closer look at the problem that we're solving. So this is kind of a graph where you have, on one axis, you have the time, and here it's like the server load. And the upper line is all of the server's resources, so all of the server's memory and CPU. If you take one customer's function, let's say we're in a Lambda scenario, it's going to have peaks and valleys depending on how people use it. Now, if I take many copies of the same function and run them on the same server, I will have times when I exhaust all of the server's resources, and then times where nothing's going on. And that's not very efficient from a let's say, service provider point of view, because serverless is serverless for customers, not so much for the service providers. However, what I can do is take a different customer's function, which has a different profile. So in this case, the yellow one kind of starts already evening out the valleys and the peaks. And if you keep doing this over and over, you get to a point where the server is efficiently utilized. Most of its hardware resources are in use. There's no degradation in customer workload performance, and all of the workloads are running simultaneously on the same machine. However, to build a system like this, you need a barrier that is both flexible. You need to scale with peaks and load and and valleys and all of that, and extremely secure, because this is a multi-tenant environment. To do this kind of thing, you need to put workloads from completely different customers on the same machine, and that's what Firecracker is. It's basically the line, the border between workloads that is both agile and nimble, but at the same time secure enough for multi-tenant workloads. Okay, so let's see how Firecracker, or what makes it fit for this purpose. The main benefits or capabilities that we focused on were, okay, first of all, we need to have secure isolation, otherwise this whole system won't work. Then we need to have speed, because again, with microservices, with the serverless functions and containers, you get the situations where customers go from nothing to thousands of instances or thousands of functions or thousands of pods very, very quickly. It can be in seconds or minutes. And so you can't afford to take a long time to start a new execution environment. It needs to happen very, very fast. And then you also need to be efficient at scale. So for example, if your execution environment technology ends up taking a significant part of the whole machine, that's not efficient. And so we focused on these features, and we built the exact capabilities that we needed and nothing more. So, as I mentioned, so Firecracker itself is a virtual machine monitor, so it uses hypervisor virtualization to actually isolate workloads between each other. There's a minimal device model, rate limiting to kind of, let's say, ensure the fair usage of the host. The process startup time is 4 milliseconds, and then you can boot a Linux guest in about 125 milliseconds. And every single execution environment adds an overhead of just 5 megabytes. So you can cram thousands onto a data center grade host. A lot of, let's say, how we achieve this has to do with just making at every turn the choices to stay minimal and not do anything else except what we really wanted to do. At this point in time, I decided to put a quote about minimalism in my presentation, and I found this one, and then I realized it has like 12 words or something, and I thought that's not very minimal, so I found this one, which seems a lot more appropriate. And this is Firecracker's architecture. This is basically kind of putting what I mentioned in practice. On the left side, you can see a host, a server, running a bunch of microVMs. They're kind of different shapes and sizes to suggest the fact that you can have different combinations of memory and CPU for each and every microVM. And they're all running there, let's say, crammed together, oversubscribing the server's actual physical resources. And on the other side, on the right side of the diagram, you can see a kind of a zoom in into one of the microVMs. On the upper part, there's a guest OS, or it can be a container workload or a function workload, and then the basic building blocks that you really need: network storage, some sort of API to control the microVM, and in our case, a metadata service. It's something that at least AWS customers are used to. There's a few more, but those are the main ones, and there's pretty much nothing else. This is how we get that very low overhead. Okay, and with that, let's get to the open source part of the story. When we were building Firecracker in 2017 and 18, we actually realized we were basically building it for internal AWS use cases for Lambda and Fargate. And we realized that this technology is actually useful to the open source community. It's pretty much decoupled from the rest of all the internal cogs and systems that make up the cloud. It has a very clean API. You can run it anywhere basically, and so other people might be able to use it for isolating their own pods or containers or microservices. At the same time, we realized that we can actually show AWS customers where their Lambda functions are executed. They can go on GitHub and they can inspect the exact code that runs those functions. And so we made a decision to open source Firecracker, and we did so just 1 year ago at reInvent 2018 under an Apache 2.0 license. What's happened since then? So we've had 110 contributions from 48 open source community members as of last week. That's 18% of all our commits. We've also had dozens of bug reports and feature requests and RFC feedback, and generally, I think we've received a lot of useful input from the community. On the other side of the story, other teams have taken Firecracker from our open source repository and used it in their own projects. Some big ones are Weaveworks, Ignite, and Firecube that Sebastian will talk about. Kata containers, which is basically a way of running Kubernetes workloads with an optional virtual machine isolation. And then we also provide Firecracker Container D, which is a plugin for Container D that eventually allows you to run the containers within Firecracker microVM. And unique in OSV are microkernel / microVM implementations. And they both now have an option to run in Firecracker. And with that, I will let Sebastian tell you about how Firecracker is used at Weaveworks.
Thank you. That's not the big introduction we talked about.
Well, no.
There's going to be music.
I need to be me, right?
Smoke bomb. And now I feel let down. So, hello, I'm Sebastian. I'm a customer success engineer for Weaveworks, which means I go out into the world and break things for customers. The general idea here is that we have taken Firecracker and we have added Weaveworks' signature YAML and GitOps mess on top of it to enable you to run fun things. It's the middle button.
No, that's a different button. Big green.
The big green button. All right. So, Weaveworks Ignite uses Firecracker to run containers as VMs using magic and also some Go. That's basically it. We take YAML declarations that describe the container that you want to run, describe the VM you want to run, how many CPUs, how much memory you want, and run it on top of Firecracker using Ignite as a command line, which is sort of like running kubectl. What we've done is we've taken also the Ignite tool, which is where we bring the fire, and we've enabled it to run Kubernetes. So we take a bunch of different server declarations, combine them with Ignite, and that makes Firekube. That's pretty much the message. It doesn't get a whole lot more complicated than that, because I'm a firm believer that if you've seen one PowerPoint slide, you've seen them all. So quick shout out to the projects that make this possible. WKS Cuddle is our command line Kubernetes spin-up tool. Cluster API we use to create the clusters, so it's a generic cluster implementation and a generic cluster interface, and Footloose and Firekube. Also, a quick shout out to my man Leigh and Lucas, who developed Ignite in the first place. That enables this whole thing. And now, without further ado, we get to the fun part, which I'm going to press a special button down here, and if nothing explodes, you will see text for the hearing impaired. Oh, I have to log in now. You get to watch me type. No fainting. Cover your eyes, because I'm typing my password. And there we go. So this on the left here is the Firekube cluster spinning up. Because we only have a couple minutes, that takes about 8 minutes to spin up. I don't know if you've ever, raise your hand if you've ever spun up a Kubernetes cluster on your cloud provider of choice and got to stand there watching the wheel turn. Well, that's the rest of my presentation, is just watching the wheel turn. So what we're going to do here is we have a couple of YAML files in this side. And again, YAML files are very exciting, so you get to see them. They look like this. That's basically it. Describes a VM. But rather than spin up that one, which is rather unexciting, I'm going to do the nothing up my sleeve portion of the presentation and show you that there is no web service running on this box. And instead, I'm going to spin up, that's an O. Well, I created an alias for that so I don't mistype it too many times. I'm going to spin up 1, 2, 3, 4, 5. You're going to make a liar out of me. 6, 7, 8, 9. Hey, that's 10. Normally this takes about 8 seconds, but I guess this one took about 12 to spin up a VM and then give me back an answer. By the way, my man here spent a little time talking about server grade, data center grade servers. This here is an $80 piece of shit Chromebook that I bought using my allowance money from a large online retailer whose name starts with A, that we will not mention. And now I'm running Nginx in a VM on the host. You can see that actually I'm running on the host itself, Gallium OS, Linux 4.1, 4.16, 18. which I ripped off Chrome OS off the Chromebook and replaced it with Gallium OS. I can SSH into this running container, running VM. And you can see, without a doubt, it is running a different kernel. So it's not just running a container, it's actually running in a VM. Over here, so that you did not have to watch the giant wheel turn, you can see we are running a Kubernetes cluster. And my alias to list out, this is a list of the Ignite VMs that are running on the box. You can see that there's a node and there's a master, and also the Nginx container that I just spun up. And if this does not explode, oh, I have to do this. Pick up the kubeconfig file, and voila! We're running a Kubernetes cluster with a bunch of pods, bunch of namespaces. And your familiar workloads. Oh, come on now. In any case, you've got a master node, you've got a worker node, and they run on a cheap $80 Chromebook. Now, in the real world, we actually do have servers. We generously proportion servers. But the overhead on these things is extremely low. So you can run on your average server a 10-node cluster and beat on it as much as you like and cause as much havoc as you might want. And that is it.
OK. Yeah, I need to also press the magic button.
Magic button.
Wow. OK. So next, I'm going to talk a bit about the Firecracker roadmap. And the first thing I want to say is that for 2020, so for next year, we built our roadmap by taking into account inputs both from our internal AWS customers and from the open source community. So at some point during the summer, I think, we opened up an issue on our GitHub repository, and we collected a bunch of input from people. We put that all together with what we also wanted to do for AWS customers. Then we came up with our roadmap for the next 18 months. And this is something that we want to keep doing. We actually want to be good open source citizens and just to take in all of the inputs that we can for Firecracker. We do want to stay laser focused on our mission. So that thing that you saw at the beginning with being an execution environment for serverless functions and containers, we want to stick very close to that and not stray from that direction. But within that framework, we're very much open to suggestions, ideas, and definitely contributions. Over there, there's a kind of a snippet from our current roadmap. It's basically a GitHub project in our repository. You can go and take a look if you want to see our full roadmap for the next year. Looking back on 2019, we started the year by working on supporting additional CPUs. Currently, Intel is supporting production ARM and AMD work. We basically have them in developer preview now. And we expect that they will also be ready to take production workloads very soon. VSOC, which is a kind of a popular way to control containers through virtual machines, is also supported. And just recently, we've added two features that were popularly requested in the community, starting from a config file, so not configuring the VM with several API calls, and then additional ARM support that made Firecracker run on Raspberry Pis. Going forward, we're basically going to continue focusing on those three big capabilities that you saw in the beginning. So on the security side, we're going to continue our defense in-depth investment. We want to set up continuous fuzz testing, reduce our number of dependencies quite drastically. There's more work planned around the SecOm filter part. Besides the virtual machine barrier, Firecracker also has a let's say, a common namespace/seccomp barrier as well. And then on the speed and density side of things, one of the things that we've already been working on and we want to continue into next year until it's basically a feature that everyone can use is microVM snapshot and restore. Alexandra will talk more about that, but I just want to say before that we also want to focus on usability improvements. So while it was not visible in Sebastian's demo, at least for the first months after we came out with Firecracker as an open source project, there was a lot of questions about how specifically to run things, being so kind of narrowly focused on a single use case. We didn't support a lot of common virtual machine features. For example, you can only run with a Linux kernel which is configured in a specific way to work with the minimal environment that we provide. So we're going to keep making this better and hopefully get to a point where it's very, very easy to use Firecracker if it's the kind of tool you need for your problem. And with that, I will let Alexandra show you or tell you more about snapshot and restore.
Thank you. Hey everyone, I'm Alexandra. I'm a software development engineer at AWS, and I'm one of the maintainers of the Firecracker project. And I'm going to talk to you and demo the new feature that we're working on. It's saving a microVM state at your chosen point in time and restoring from the snapshot that gets generated. So here we go. Our first slide is about why did we do this? Well, Firecracker itself is a building block, just a small part in a big ensemble of moving parts of complex execution environments for serverless and for containers. And we figured that a natural next step and a next block for these serverless and container environments would be this capability to snapshot and restore from that if you don't need a VM anymore, but you want to keep its state around and save it later. At AWS, 90% of what we build are explicit customer requests. And the remaining 10% are things where we might not get that specific ask from a customer, but we use what we know from interacting with them and from the feedback we get to try and invent on their behalf. And the snapshotting feature is a little bit of both, because we did actually get this specific request from the open source community in our GitHub repository. And we also kind of thought how this might be a good next step in empowering new features in the customers that use Firecracker. And there's another reason we did it. Last year at reInvent, when we open sourced Firecracker, its speed was one of its key points. It's because you can fire up a full-fledged Linux guest in as little as 125 milliseconds. That's pretty fast. But it got us thinking, can it go any faster? And yes, it can. Boop. This isn't very visible, but this VM took 125 milliseconds to fire up. So that's the time you get from a bunch of files on disk to a live guest. So in order to get one of these VMs, you need to start a new Firecracker process that fires up a new REST API. You need to shoot commands into that REST API to configure how much memory it's going to have, how many CPUs, what devices it should have, and then issue a REST command, another API call. And from that point on, until you can actually enter user space init in the VM, it's 125 milliseconds. Now, if instead of going through all of these steps, you snapshot your VM after it's already done what you needed to do, and all the devices are configured and everything, with just one API request, load a snapshot, the time to get from that bunch of files to the running VM goes from 125 milliseconds to 5. It's 25x improvement on the same VM. So if I want to replay that in a relative fashion, this is how long it takes you to configure a VM, while snapshotting and restoring from that is basically almost instantaneous. So how come it's so fast? Well, one of Firecracker's core tenets is its minimalism in features. And that translates into there's not a lot to save and restore in the first place. What you need to save and restore later can roughly be broken down into 3 categories. First, there's some internal state of the VM itself. It's the data structures that it uses to communicate with the underlying KVM hypervisor. So you can think of these as like registry values, pending events on the vCPUs, the state of the interrupt controllers, and so on. Then there's the device state. Like I said, there's not a lot here. We have a very minimalist device model. Firecracker supports PIO devices and MMIO devices over VirtIO. The PIO are a super minimal keyboard implementation and a serial console. And those are considered stateless, so that's nothing to save. And on restore, it's recreate new ones. As for VirtIO MMIO devices, we support block, net, and vsoc. And we do save their states and restore them later. And you can think of their states as half user-facing. Like for block, that would be the path on the host to the underlying file that emulates the block device. And for network, it would be the name of the tap device on the host that emulates the network device in the VM. And that's pretty much it. You save that and restore it. And the third thing is the guest memory. That can be however much you want. And this is a design decision that we took when we started prototyping snapshotting. If you go to mainline Firecracker, in the upstream GitHub repo, you'll see, if you inspect the code, that Firecracker uses anonymous RAM to support its guest memory. And if you were to save that, you would need to dump all of that into a file. Instead, a snapshotable VM is going to use a memory mapped file. So all of the pages that the guest dirties are eventually going to get written to that file. And pretty much that boils it down to the guest memory is almost all already there. And if you flush it, it's all going to go in that file. So again, it's a simple process, as simple as it can get, and it's in line with Firecracker's tenets. Now let's look at the steps of creating a snapshot. First things first, stop the VM from running. You need to freeze the vCPUs before starting the save state, because otherwise the VM is going to continue running and alter that state inside the guest while you're saving it, and you're going to get an inconsistent state in your snapshot. So pause vCPUs first. After that, the VM's not running anymore, so we can start churning its state. We take the internal data structures that I mentioned earlier for talking to KVM, like the events and the registries and all of that, serialize them, store them for later. We take the devices that we do serialize, so not the PIO, just the block, net, and MMIO devices. And we save what we got from the user, like the path to the block device on the host and the name of the tap interface. And we also get the internal virtIO MMIO state of the devices. So that would be the negotiated features and the config space. And we serialize those too, save them for later. Now, at this point, there's nothing more configuration-wise to save. We can just dump all of that information into one file, and we get half of the snapshot. The other half is the guest memory. That's already a file to begin with. And since there are likely dirty pages still in the page cache from what the guest has been doing, we flush those. The guest isn't doing anything anymore because it's paused. And there you go. You have your second file, the second half of the snapshot with the guest's full memory contents. And it's a sparse file, so it's only going to be sized to what the guest actually dirtied. It's pretty amazing. The last step is another design decision we took. Is that terminating the VM after we're done with it. That's because the use case we had in mind for snapshotting is you're going to snapshot this VM when you don't need it anymore. And when you do, it takes 5 milliseconds to get restored. So you can save it for later. Here's a visual representation of that. Let's say you have a Firecracker microVM that's fully configured. It has an API endpoint. Does this thing work? Yeah. The PIO devices, the console and keyboard, the MMIO devices. In this example, we have a block and net devices, 2 vCPUs, and guest memory. Now, all of these are configured through individual API calls. Machine config is going to tell you how many vCPUs you have and how much memory, drives, going to configure the block devices, network interfaces. Well, you figure that one out. Start the microVM, let it run until you're happy with the state and you want to snapshot it. You find that this would be a useful point in time. And then issue a new API command, create a snapshot. What this is going to do, whoops, first pause the vCPUs and save their state. Then serialize the block and net states, add them to the vCPU state and the internal KVM facing state that I mentioned earlier, save them to a file. And this is already a file. So just sync it, and it's already there. And last step, when all this is successful, the VM dies. Now what about restore? What happens when you want to use that snapshot? Well, first things first, some integrity checks. Note that you can add your own encryption and checksumming and whatever external integrity checks you want outside of Firecracker. What Firecracker does is verify that these snapshot files look like snapshot files. So they have some state in there, magic numbers, and all of that. If everything's OK, the guest memory, which is already a file, gets memory mapped and saved there for later. The vCPUs are recreated. Their number is read from the state file. And they get loaded up with the state that was saved. And they're not started just yet. Then the devices are read from the snapshot and deserialized. The PIO devices, keyboard and serial, are created from scratch. There's no state saved there. The MMIO devices are recreated and loaded up with whatever we saved. And then we already have everything we need for a VM. We can just resume it, kick the vCPUs back into running, and it's going to start paging in from the guest memory file whatever it needs to run. So we're going to start with an empty VM, a Firecracker process that isn't running anything except for the API thread. We have our snapshot composed of these two files. First things first, the integrity checks. Everything's OK. We can recreate the vCPUs, load their states, and leave them there. We recreate the MMIO devices and fill them up with the deserialized state. Recreate PIO devices from scratch. Memory map the guest memory file, and let the vCPUs run. And there we go. We have the same VM like nothing ever happened. And now it's time for the demo. I'm going to start with a variant of the demo we did last year at reInvent for Firecracker that starts 4,000 VMs on the same host. And each of these VMs runs a small network workload. Let me just SSH into everything. I'll push the button. So each of these VMs is going to run a small network workload. It's going to start up and do some traffic. And we're going to visualize that traffic. First, this is going to go with normal Firecracker. And then I'm going to resume 4,000 VMs. And it's going to go a lot faster. And we're going to see how the workload differs. OK. I'm going to push the magic button. Oh my God, it actually seems to be working. OK. Let's configure this. This script is going to set up some general parameters and 4,000 network interfaces for the VMs to connect to. And on this side, I'm going to fire up a visualizer. So that screen went gray, I guess. And each of those tiles, that's a heat map, is going to represent a VM doing workload. Now let's see what that actually means. Start many from 0 to 4,000 on, let's say, 6 threads. And if you see on the, where did I put the thing? On the right side, these snake-like formations are the 6 threads that I started in parallel. And all of them are firing up VMs. Each VM wakes up, does one iteration of its network workload, goes back to sleep for a random amount of time. And after that, it wakes up, does some more traffic, and so on. So each tile in this heat map gets a color depending on how much network traffic is flowing through it. We have an iPerf server running on the host for each VM, connected to the tap device that emulates an VM's network device, and the iPerf client inside each VM doing random traffic and then sleeping for a random amount of time. You can kind of see that they're all starting, doing something, going back to sleep, and then randomly waking up and doing some more. All of these VMs are running on Alpine Linux. All of them have one block device where the root file system sits, and one network device that they're using to do this traffic. So their serialized states contain serialized devices and serialized internal data and guest memory. I think they each have 2 vCPUs and 128 megabytes of RAM. But a memory snapshot file is actually much, much smaller. It's between 20 and 30 megabytes depending on how much that VM has paged in. So the size of the snapshot varies greatly depending on what your VM is doing. So if you have like a Java or a garbage collector inside that's going to dirty a lot of pages, then you are going to get a large memory snapshot file. But these VMs don't do much. OK, so they've all started up in less than 2 minutes. And yes. Oh, no, it disconnected. It's back. So they all started up in less than 2 minutes. And now I'm going to do the natural thing and kill them, but not before we take a quick peek at the memory usage. So 4,000 VMs started from scratch, not from a snapshot, are taking up 153 gigabytes out of the 500-ish that we have available. CPU is fine. They're not doing a lot again, but they are using up a heck load of memory. So let's kill them. And we can see them slowly starting to die. There we go. They're all done. The memory is still, the memory consumption is still pretty high, but I think that's because, there we go, the memory went down 1-ish gigabytes, and you can see now that the largest memory consumers are this Python script and systemd. So now I'm going to resume 4,000 microVMs, 0 to 4,000, also on 6 threads, so we can see that we no longer see the snakes. Why? Because each of these VMs was snapshotted while it was doing traffic. So it could either have been during an iPerf invocation or during a sleep. They were likely snapshotted during sleep, because most of them are sleeping. And that's why we no longer have the situation where they wake up, do traffic, and then go to sleep. They wake up and then they might be mid-sleeping. So they're going to start doing traffic at another random point in time. I've started these VMs from 4,000 different snapshots that I already had prepared. And I would have put the saving of the snapshots in the demo, but we'd have been here for a while, because while the resume is super fast, orders of magnitude faster than booting a fresh VM, the serialization and the writing and the syncing of the guest memory has been known to take up, in this prototype, about 70 milliseconds. So still a lot faster than booting a fresh VM, but not as fast as resuming it. Oh, so it's already done in a little over a minute, and the script is still active because it's parsing at times, because I want to show you a little graph of how much faster resuming is than booting from scratch. In the meantime, let's examine the memory. So remember that 4,000 booted VMs were taking up 150-something gigabytes of RAM. Now we have 14.8, less than 15 gigabytes with 4,000 live VMs. If you do the math, that's less than 4 megabytes per VM. And this is a full-fledged Linux guest doing network traffic. So 4 megabytes of Firecracker device model, so all the overhead of the Firecracker process, plus all of the memory that each guest is using, is less than 4 megabytes. And the memory consumption is low The CPU is still next to nothing, even though they've been paging in like crazy. So this can be a powerful tool in increasing density. OK, looks like I got my my data parsed, so I'm going to copy it here. Firecracker demo. I'm going to i3 metal, Firecracker demo. It's a log file with all the times. Oh, no. What did I do? Well, now it worked. I'm going to plot it. OK. Let's look at the plot. In orange, we have the VMs that booted from scratch. You can clearly see the 6 threads that ran in parallel. And in green, we have the VMs that were started from snapshots. You can also see the 6 threads here, and they're pretty much in tandem with their sisters above. But there's a big difference. So the very first one looks like was fastest to boot, just 100 milliseconds. And the laziest guy took 191, which is still pretty good. And you can see that at the point that this VM booted, the host was already pretty crowded. In the meantime, resuming took 2 milliseconds for the first one and 38 for the laziest one, when already there was some crowd of microVMs on the host. So what was the host doing when this happened? It was paging. It was page faulting because the guest memory is a file. And the guest was waking up, trying to do traffic, and getting the pages from that file into RAM. But once that's done, there's no more CPU contention on that side. And the guest has only what it needs. And that's 10 times less RAM than in this scenario. And that pretty much concludes my demo. So I don't know what we do now. I think we can move back to the mainstream presentation. This was the demo.
Yeah. So I guess this
pretty much wraps it up.
This wraps it up. Just a quick call out if you want to learn more about the stuff that's going on in this space. So there's another presentation, OPN402. That one's about RustVMM, which is a open source community that basically the Firecracker team is a part of. And along with other teams from other companies, we are taking building blocks for virtualization, for virtual machines, for things like that, and making them available for anyone that wants to use them to create other virtualization projects. Then there's a couple of builder sessions where basically Alexandra will show you the ins and outs of how this demo works and basically how you can use snapshotting in a real use case. And finally, there's another on the containers track. Container 408 is a session about Firecracker Container D, and it shows you how you basically get to run I guess pods or container groups within a Firecracker microVM isolation boundary. For Q&A, will actually be available after the session, so we'll be around until our time expires, which is about 10 to a little bit over 10 minutes. Yeah, and that's it. Thank you very much for attending.
One last thing.
Oh.
We have a whole bunch of Rubik's Cubes over here if you like Rubik's Cubes or you have kids or you just want to throw them at somebody. Hopefully not me. But feel free to come up and take some conference swag.
So we'll just close the session now and just be around here for all your questions. We're not running away. Please complete the survey at your earliest convenience.
There's a test? My goodness. Yeah.